All right, so this week we are going to talk about AC. It's kind of a different week. I like this week. I don't know why. It's actually a very difficult week to teach. And it's kind of a difficult week to be a student. But lots of maths. Lots of maths. 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 Just here for what? All right, so I'm hoping at some point in the past I might have mentioned a little thing called Ohm's Law.
What?
I know. And you were hoping that even though I said I was going to build upon that I was lying, but we were going to build upon that. And then just like this week, we're going to talk a lot about AC and how it's used, and we're going to build upon that pretty much through the rest of the semester. So try not to get lost. And like I said, there's going to be a lot of math, and you just got to stick with it and do it. For some unknown reason, the FAA does not concern themselves or concern you with parallel problems in AC. So we're just going to stick with series and hope that everybody can do what's asked of them. Yeah?
Are we going to phase any parallel?
Yep. Yep. We're going to go all the way through phase angle. Is that what you mean?
Okay.
Absolutely. That's all part of it. So alternating current. So AC, alternating current. We could say theory. All right, we're off to a good start. AC, alternating current theory. Well, what is it? It is a current that periodically changes direction and continuously changes in amplitude. And that is opposed, so as opposed or compared to, as opposed to DC, which stands for what? Direct current that never changes direction. Or magnitude. Well, kind of does. As the battery drains, it certainly gets lower in, I should say, magnitude or amplitude. So where can I get true DC power?
Battery?
Yep. True DC is only created with a battery. You can create DC with the use of mechanical means. Of course, you know your car has DC, right? You got an alternator, that makes DC. You have a generator, that makes DC. You can use rectifier, that's going to make DC, but it's not true DC. I mean, it is, and we call it that, but so I want to be careful how I say true. It's absolute DC, where it's a solid, flat line. If you take any other means and put it on an oscilloscope and you zoom in far enough, you'll start to see the waveforms because it's not perfectly. There's some ripples and stuff in there. Let's see. All other electricity produced from mechanical means is AC converted to DC. So all other means, well, all other electricity, that's what I should say. All other electricity produced with mechanical means. What does that mean?
Turning mechanical energy into electrical energy.
Mechanical energy into electrical energy. So what are those devices? Generator, alternator. They start like generator produces AC, all of them. Alternator produces AC, all of them. It doesn't come out that way though. So it's converted inside to DC. So all of the electricity produced in mechanical means is AC converted to DC. And I will show you how that's done when we get to generators, I think. No, I'll do it in a few minutes. Gotta remember if I do it now or later. So, all right, AC. AC has some advantages. AC has advantages. Quite a few, actually. One, voltage can easily be changed. Easily be changed by transformers. Talk about transformers next week, I believe. But we take SMUD around here. I can't say PG&E since they're shutting power off anyway. So SMUD, all right, comes out of Rancho Seco, well, not anymore, but comes out of the power plant, and it's super high voltage. I don't even remember what the numbers are. What are they? 12,000 volts or something. All right, but we have 120 or 110 coming out of the wall. So they produce super high voltage with very low amps, relatively speaking, and that goes to a transformer. The transformer steps down the voltage but increases the amperage. So you can do that real easy with transformers. You can't do that with DC because it's too steady. So the fact that AC is constantly changing allows you to use a transformer. AC motors can be produced in three-phase systems. These can be three-phase systems. Maybe I should say can be used in three-phase systems. It's also called polyphase, meaning multiple phase. So you see polyphase, that means you can use that for three-phase or two-phase. I don't know if there is such a thing. Allowing the use of smaller motors. So the motor physically is smaller, weighs less, but it takes three-phase. That's a good thing. AC generators are more efficient. Than DC. And one of my favorite here is wire. Wire used in AC can be much smaller. Due to increased voltage. Due to increased voltage. I like this example. You don't have to freak out, I'll just tell you. A 1 horsepower motor that's 60% efficient, driven at a distance 100 feet. I'll just write this in. So it's 746 watts. That's 60% efficient. Driven a distance 100 feet from voltage source. VOLT from voltage source of 10 volts. So if I want to figure out the wire size for something like this, where would I go to? The table that's in AC 4313. So I figured this out, and it would require, first of all, I'd have to do some Ohm's law. It would have required 125 amps, and this would call for a number 1 wire. Number 1 wire, is that big or small?
That's big.
That's pretty big. 100 feet of number 1 wire weighs 25 pounds. Do the same thing with a 200 volt AC system. So 200 volt AC, same thing, needs 5 amps, which uses a number 18 wire. which is very small, and that weighs 1 pound. So just save 24. Yeah.
So what you're really saying is that the voltage drop in AC is less because it's higher voltage?
Yeah.
So it doesn't
I don't know if I'm saying that. I'm just saying it needs a lot less amps.
So it's more efficient.
Yeah.
Okay.
I mean, it weighs less.
Got it.
It's 1 pound.
Huh? 1 pound. So you can do that whole thing for 1 pound. So you can save 25 pounds on one motor, 24 pounds. All right, see if I can find a PowerPoint here I want to see. We'll go with this one. Hey, we're going to cover this more when we get to generators. So we get to generators, I'm going to pull up the same PowerPoint. And I'm going to go, hey, look at this. Remember this? And you're like, oh yeah, I didn't understand it then. I don't understand it now. So, well, there's content. Who knows what that is? All right, slideshow from beginning. All right, alternating current. Well, first of all, we can look at, I like my little drawing here. Direct current looks just like that on an oscilloscope. It's just a line going straight. Doesn't go up or down. But alternating current goes positive then negative, then positive then negative, and positive negative. So I said that it does what? It's periodically changes direction. So this is one direction, this is the other, and continuously changes in amplitude. This is the amplitude. See, it's constantly changing, and this is time as we go. All right, why does it do that? So we'll just kind of have some fun with this. How is voltage induced? How is voltage induced in a conductor? Need 3 items to generate current flow. Care to guess what those 3 items are?
Coil.
A magnet, a coil. Magnetic field was correct. Number 2, coil of wire, conductor. And 3, motion. Okay? If you have those 3 things, you are going to get electricity. Case in point. I made this when I interviewed for this job years ago. They actually asked me to teach on, how does a generator work? And so this is part of it. And I thought, I should just make a silly little generator. And so I tried to make it look as silly as I can. I just found some stuff from the garage. These are magnets in here. And so a Tinker toy I stole from the kids, and a nail and something else, right? And so hit the light. So it's just a magnet, a bunch of wire, and something I can spin. So.
All right, Tim, hold on.
Yeah, it's my flashlight. Now I could hook it up to a drill that plugs into the wall. That would work better. But anyway, you can turn the lights back on. So it's just magnets and some wire. And so I'm just spinning these magnets across some wire, and the little thing lights up on the end.
Wait, is that AC
What is it? Is it AC or DC?
It's AC, I think.
Well, it's a good question. So we're going to find out in a minute. All right, so you got to have relative motion. So I could just take a magnet or a wire and just kind of go up and down really quick, and that, of course, would not work well because that is just ridiculous. So this is not very practical. Huh?
It would theoretically work.
It would theoretically work, but you would get tired. It's just not a good way to do it. So the solution here is to loop the wire, and that's called an armature. Now, my little thing is backwards because I move the magnets while the wire stays constant. But in this example, we're going to have permanent magnets that are stationary, and we're going to move the wire around. All right, so you have to kind of pay attention to some nuances here. So with this right here, these are called slip rings, these round tubes. And that slip ring you can think is welded to this bar coming out. And this slipping right here is welded to this bar. So this one right here does not touch this first bar, it only touches the second one. Follow? Okay, and these right here are called brushes. And they're made out of carbon, and they're rubbing against here, so electricity can actually flow through my resistor. So here I have a continuous path for electricity to flow. So it can start here, come out through here, goes this way, up through, around, back over to here, and out. All right? So if I rotate that, I want you to appreciate the animation that I have created in PowerPoint.
So awesome. Literally going one way and the other.
It's literally just 2 slides going back and forth, but makes you think it's going. Anyway, all right. Well, talking about the whole thing is based upon a generator, and a generator produces what? DC. So it's supposed to produce DC. So there are many, but this primarily will produce AC voltage, which is what we're just going to look at right now, is how does we get this AC. So the reason why that this works the way it does is here we have some magnets, and I don't know how well you can see pretty well that we have lines of flux. All right, so lines of flux, that's the kind of the invisible power, if you will, between magnets, the attraction. So it's actually there. And so we can do a lot with magnetic flux. But you can see that the density, represented here by the lines getting closer, is the greatest right in here in the middle between the north and the south magnet. And the lines of flux are going parallel, and the greatest voltage occurs as the conductor passes at right angles to the flux. So as long as this loop right here is coming up in this way, it's actually producing the greatest amount of what's that? What's that? Usable power, yeah. Usable power. This one's going down, that one's going up. In a second, well, I think my next slide shows it. Yeah, it's right there. So that's the least voltage is going to occur. The least potential is right here because it's going parallel to the lines. Everybody follow me so far? So if we go back one, we'll look at, this is the greatest, and notice that here's where the loop is. That's the least. Notice where the loop is. All right? But, oh yeah, determining the direction of current flow. So we have to figure out current flow. It's a left-hand rule. I don't make you memorize left-hand rules or right-hand rules because there's so many of them, and then it's just like, it's ridiculous. But anyway, in this case, we'll say the thumb points in the direction of motion, right? It's going to go like this. So right angles. It's a gang. It's going to be our gang sign. Okay?
Gang sign,
Yeah. Ohm's law, yo. All right, so.
Catch me on main campus.
All right. Field. Pointer points in the direction of the field from north to south. Okay, the way I kind of remember north to south is I think, well, the Earth has a magnetic field built up in it, right? And that's how compasses work and stuff. And so for me, it's kind of, I think, what comes out of the north and it falls down outside the world. So north to south, it's false, but it works. All right, north to south. And the middle finger points in direction of current flow, negative to positive. So what flow is that, conventional or electron? All right, electron flow through. And that's why I don't make you memorize these, because what would happen if we went to conventional? Then I guess we'd have to go this way. And it becomes a right hand, so left hand. So it's like, yeah. All right, so if we keep that in mind, we go back to looking at this. We've got, all right, which way will the current flow? So I've got thumb points in what?
North. Direction of movement.
Direction of movement, okay. And pointer is what?
Current.
No, pole. From
Magnetic field.
magnetic field.
Pointer points in direction of field, north to south. And the middle is going to tell me direction of current flow. So I'm going to ask you which way does the current flow. So it's going to be this finger right here. It's going to be current flow. So direction of movement, point from north to south, right?
Uh-huh.
Okay, so which way is current going to flow?
All right. Towards us.
All right, from negative to positive. So we're going to go out of the screen towards you. Direction of current flow, out of the screen towards you. All right, that becomes important because when we come back and look at this, we're going to look at this drawing here, and noting that, we can figure out why current is flowing this way through this armature. So because we point from north to south, all right, this is the one that's kind of backwards. So north to south, direction of movement, and so this loop is going up, therefore current flow has to go back around that way, right? Okay, so note in this particular case that current flow is coming through here, around here, out this brush, through the load, back into this brush, and back around. And this is loop A. Loop A is going to stay consistent with this. This little piece right here is going to be loop A. So now loop A just went around, and now it's over here. Not loop A, but loop A. So, yeah. So loop A is back over here now. I'm going to go back one. It's here. So remember that it's coming around this way, and our current is flowing through the load down this way, right? Everybody follow that? Down this way. Now it's going back this way. So a minute ago it was going this way. Now it's going that way.
Wait, do that fast a couple times. Oh, perfect.
It's the animation. All right. There they are back to back.
Kevin, can you clarify the motion? I'm not
Yes.
following on that.
The motion of what?
Whatever of, I don't know, motion of something.
This right here is spinning around.
Remember the animation? No, seriously.
This loop
oh,
of wire.
I see. Okay, it's
Loop
actually
of wire
okay.
spinning around just like that. Okay?
Okay.
So while it's in this particular plane, it's flowing this way, around B, out here and around. Okay? Loop A just went over to here, but still it's going around this way. But because of the way these are wired down here, it comes down to this one now and out here and went backwards. All right, I'm going to put it all together. It's okay. All right, so side by side. Yeah.
What happens when while it's at the angle? It's switching.
Nobody knows, Steve. I'm going to get there. It's a good question.
That's when it's zero.
I haven't thought about that. It's going to be 0. All right, so
Nobody knows.
this right here is, of course, max register, max voltage, and then I'm showing max voltage here, so it's max this way and that way. Everybody follow so far?
I saw it.
All right. We're going to put it together here. So what we just learned, well, hopefully, the greatest voltage is produced as a conductor moves at right angles to the line of flux. Left-hand rule shows us current is reversing direction. We can understand the following. Yay, this is putting it all together. I think this came out of your book, actually. So at this point where the loop is straight up and down, remember that now the loops are practically going parallel to the lines of flux. And so we get 0 voltage. And then as it rotates around and starts to cut, it rotated around, and now B came down here and A is coming this way. Current is flowing through here, out this way, and down. We'll call that positive, so it swings positive. It's going to continue to rotate until we start to diminish and get to 0. Here's my 0 point. Then as it rotates through again, it's going to start to build up, but this time it's going to go backwards and go the other way, and we'll call that swinging negative. Then it goes back to 0. And just keeps repeating that, and that's why we get AC. Just that loop spinning round and round in there. Goes 0, full register, 0, full register, 0, full register. But it also goes forward, backwards, forward, backwards. Yeah.
Could you explain why it goes down again?
Why it goes down? Because when it goes from here and starts to twist towards, it's here, starts to twist up, now the loops are going parallel to the lines of flux. And it's not cutting a line of flux, it's flowing with it. And if you flow with it, a wire flows with the lines of flux, we say it doesn't cut it, and so there's no change, and you get no voltage. So it'd be like, we go back here. It's important to note that, all right, in this wire right here, I have to go up and down. If I go right and left, I get nothing. It's got to go up and down. I want to see the animation again. Is it going to work? There we go. All right, so the loop is rolling, right? So you get no register, full register, no register, full register, no register, but every time it does it, it goes this way, now this way, now this way, now back. Follow? Okay. All right. Oh, forgot about this. It's way out of a sequence, but anybody know what this is from?
Yes.
Yes, we're going to talk about vectors.
Hang on a second. You wouldn't show the Family Guy episode.
There's a big difference between Family Guy and vector. We're going to talk about vectors. So when we get there, this is just going to make a noise and it's not going to work, and so.
So it's kind of like that.
See, I got. All right, we're back on the microphone, hopefully. Who knows? Okay, so vector is a little out of line. But, all right, so let's see. How is AC produced? Well, how is AC produced? How is AC produced? All right, so then I went through my whole PowerPoint. I'm just going to write PowerPoint slides. PowerPoint slides. Because I'm not going to write them all down. Because we're going to get into that. We get into generators. Wow, wrote a lot.
Is your PowerPoint on Canvas?
It's not, but if you remind me at break, I can put the PowerPoint in Canvas for you. All right, which brings me to point three. Point three. Well, we started by an opening slide that had waveforms. Let's look at some different waveforms. And waveforms is really what you're going to see if you look at an oscilloscope. And an oscilloscope is it's a very large. I'm trying to relate to you guys. I would say it's a TV, but now I'm thinking it's a smartphone that's very large, but has a small screen on it, and it shows you what AC looks like, or any type of current form or voltage form could look like. And you know what I'm talking about because you've seen them in the lab now. So, all right, waveforms. Well, there's many types of waveforms. Many types. And if we look at some of these, we could say, well, what is DC?
Can you go back a little bit? Thank you.
You spent too much time watching Vector, didn't you? So if I plugged a DC, and where do I get DC from? Batteries. Batteries is a true DC. And I plug it into an oscilloscope, I would get, except straight, a line that's very straight. Direct current. And it's not going to really move unless something weird is happening, like the battery's dying or... All right, there's chopped DC. Chopped DC may look like... You can actually do this with your oscilloscope. It's got something built in. Still direct current as long as this is the zero line and it's all positive. It's pretty much direct. It's not changing. It's changing in amplitude a little bit, but it's not really changing direction. And then we have, well, we're going to talk about AC, which is also called sinusoidal, where this is the zero line. That's zero. And it goes high, swings up, and it swings down. It swings up, and it swings down. Sinusoidal. All right, one cycle. So one cycle is it's a complete cycle, and you can really start it wherever you want. I'm going to say one cycle is from this point right here where it crossed the zero line. That's half a cycle coming around right there. So that right there is one cycle. Like I said, you could really, as long as you find a spot that's the same, like I could say from this peak to this peak, so to speak, is a cycle. I don't like that one. But it's 300, no, that's not 360 degrees. So I go from here to here, it would be a cycle, sorry. So there would be a cycle, but you have to find the peak, and you have to be accurate. So when you work with the oscilloscope, you're going to find out that you can move the waveform up and down and back and forth, and you have to be very careful on how you do it so that you can actually find the correct cycles. I'm going to write more on that in just a second. So here we go, B. One cycle of AC is from, well, no, it just looks ugly. From, let's say 0 volts to maximum in one direction. Returns to 0, turns to 0, increases to a maximum,
Did you say that was 1 volt OV?
No, 1 cycle is from 0 voltage to maximum. Here's maximum in one direction, returns to 0 right there, increases to a maximum. Turns to maximum in other direction. In other direction. And then returns to 0 and returns to 0. So all right, looking at this, starts right here, starts at 0 voltage, goes to a maximum, which is right there, goes back to 0, goes the other direction to maximum, returns to 0. That would be 1 full cycle.
Okay.
Yeah.
Is the 0 voltage equal to like the 0 degrees or not?
Yeah. Yeah, I'm going to show degrees in just a second. So that's good. That's good. So, all right. So if I redraw this down here, a little bit more room. I'll try and make it nice, but who knows? We'll make this 0 volts right here. Make this the 0 volt line. All right. So it starts here, goes up, comes down. Up. I'm doing all right. Goes down. Back. All right. So if we look at this and we think about how that loop was turning inside of those magnets, then we can think about degrees. So right here, that's 0 degrees. This right here is 90 degrees. So the loop started at 0 and it rotated half, so that's 90. Comes around to 180. That's going to be right here at the 0 line again. So 180 degrees. What am I going to have here? 270 degrees. 90 degrees. 270. Back to 0 right here. 360 or 0 degrees. All right, back to the beginning. All right, so from here to, this is my 0 line. From here to here is what?
1 cycle.
Okay. 1 cycle. From,
Could your 180 degrees ever be 0?
well, it is, it's 0. Well, it's a random thing.
Okay.
I mean, if I just started in the middle of this giant waveform, like if I plug it into the wall that's been running for years, and just pick a spot, then it's just whatever, make it at that point. It could be 0 or 180. So you can't really tell. I just arbitrarily made that 0. All right, so from this line to this, that's called the peak. And of course, carry this over, and here, from here to here, is peak to peak. Peak to peak. So I'm going to move this down a little bit. So we had 0 volts at 0 degrees. We had peak at 90 degrees. We had 0 volts at 180 degrees. And then we had a negative peak at 270 degrees, and then back to 0 volts at, we'll say, 360 degrees.
Negative peak?
What?
Negative peak?
Just 0, 0, 0, 0. Yeah, so it's a negative peak because it went down
Oh, yeah.
and then 0 it up. All right. The number of these cycles that we just had right here from 1 cycle, the number of cycles per second is called frequency. The number of cycles per second is the frequency. Also called hertz. So 1 hertz is 1 cycle in 1 second. So 1 hertz, hertz also called Hz, hertz. 1 hertz is 1 cycle in 1 second. Standard US electricity, that's house electricity, is 60 hertz. So 1 cycle is how long? 1/60th of a second. So you get 60 cycles in 1 second. So therefore, 1 cycle is 1/60th, or 1/60. Common aircraft, AC is 400 hertz. Oops, sorry. And it can range from 360 hertz to 900 or 800 hertz. One cycle may also be called or referred to as a wavelength, as a wavelength, like 1 wavelength. All right, I will stop here and give you a break.